Well, hey there, everyone. Today we're going to be looking at the AP Statistics Practice Test, questions 11 through 20, and I think we better just get started. Number 11 here says, a sample was taken of the salaries of 20 employees of a large company. The following salaries in thousands of dollars for this year, the following are the salaries. Suppose that each employee receives a $3,000 raise next year. So basically, each employee's salary is increased by $3,000. Well, what's going to happen to the IQR range? So the way that I want to look at this is to kind of take a look at this before and after here. Now, this before is I went ahead and put all of these salaries into Staplet and had it create a histogram, not a histogram, a dot plot of all of those salaries. So this is before. This is the salaries as they're written here. And then I took and I added $3,000 to everybody's salary. And I want you to take a look at these two shapes here, the one on the left and the right, over here and over here. They're basically the same shape. The only difference is that this one right over here, this lowest is 30,000. That's about, this one's 31,000. And over here, the lowest is right here. That second dot that we were looking at is right here. That's 34,000. Over here, the maximum, I think it looks like 77,000. And over here, it's 80,000. So really, it's the same distribution, just kind of brought over to the right 3,000 units. So there's nothing different about the two shapes. They're exactly the same. They're not compressed or extended in any way. And furthermore, if we decided to compute the IQR, well, that would be the subtraction of these two numbers. So maybe we can do that really quick. That's 60 minus 39. That's what, 21.5. Over here, we can kind of do the same thing. Q3 minus Q1. Taking here a look at the right side of the after scores, you might have noticed them change a little bit, made a little bit of a mistake. But if we take those two and we subtract those again, that's again 21.5. So 21.5, 21.5, these are exactly the same IQRs. So that's good to know. The IQR is actually going to be unchanged. We know already that this is the answer. And we can take a look at these other choices over here. Increased by 3,000. Of course, that's not going to happen. Multiplied by 3,000. Yeah, we already know what the correct answer here is. But before you go and really waste your time going and putting all of these distributions into your calculator, of course, you always could. There's nothing wrong with that. You're just going to lose a lot of precious time. Whenever you raise or lower all of the numbers in a distribution, all of the measurements, the IQR isn't going to change. And basically, that's because the relative distance between Q1 and Q3 is only going to be increased or lowered by the amount that you're adding or subtracting. The only way to change measures of variation, that's the IQR and the standard deviation, would be to multiply or to divide all of the numbers in the distribution. That's the only thing that's going to change the IQR or the standard deviation or any measure of variation. So with that, we can go to number 12 and says you can roughly locate the median of a density curve by I because it is actually the area on the left and the area on the right are exactly equal to each other. 50th percentile, if you think about with a density curve, in a density curve, the area is exactly equal to the proportion or probability. So in a density curve, 50% would be on the left, 50% of the area is on the left, 50% of the area is on the right of the median. That's often kind of mixed up or conflated with the mean. So the mean is the balancing point of the curve. So let's take a look at this. The point at which the curve would balance if it was a solid material, that's going to be the mean and not the median. The point that divides the curve into two equal parts, that looks like our winner. I'll highlight that for us. The point where the curve reaches its peak, no, this is the, oh yeah, it's just the peak. The point where the curvature changes direction, no, that's not correct either. In a normal distribution, that would be the location of z equals 1 and z equals -1. And the point at which the height of the graph is equal to 1, that just kind of sounds good, but it really doesn't have anything to do with what we're talking about here. So this is our correct answer choice. It's the point that divides the area under the curve into two equal parts. We can take a look at number 13. Which of the following are true of all normal density curves? So this is very important. All normal density curves are in fact symmetric because they have the exact same shape. Okay. The curve reaches its peak at the mean. This is true as well. And 95% of the curve is within 1 standard deviation. No, and this one is not correct. Within 1 standard deviation is approximately 68% of the area. So it looks as though 1 and 2 only would be the correct answer for number 13. Number 14, we have kitchen appliances. Well, they don't last forever. The lifespan of all microwave ovens sold in the US is approximately normally distributed, with a mean of 9 years and a standard deviation of 2.5 years. What is the percentage of ovens that last more than 10 years? So we're keying in on this normally distributed because whenever you see normally distributed, that needs to key to you that we're going to be normalizing and finding area for the most part. So we have the z-score is equal to the number minus the mean. Our number is 10 years. The mean is 9 years. The standard deviation is 2.5 years. That's equal to 0.4. And then now over here, the way that you would write this is the probability that x is greater than 10 years. You could probably even write down microwave life. Micro is greater than 10 years. That's equivalent to z being equal to greater than 0.4. On your TI calculator, you would get to second vars, which is a distribution menu. Go to normal CDF, and then we want to know, let's see, we want to know more than 10 years. So we're going to go 10 years to really this is infinite, so 1e99, or just put a really large number in there. The mean is 9. Standard deviation is 2.5. We can paste onto here, and that gives us about 3445. Now all of the stuff that I'm writing down here at the bottom, all of this stuff right here, this is really what you would be doing for a free response test. I know I'm, kind of preparing you for a multiple choice test, but you really should know how to do this as well. So I'm just going to go ahead and do this. So we have a z-score of 0.4. So we're going to locate that on a normal distribution. 0.4 is a little less than halfway to 1. We're just going to put a point there, and then we're going to shade all the way to the right of this. Now down here at the bottom, we only need a couple of numbers. The first number that we would need would be the mean, which would be 9 years. And then the next number we need over here is 10 years. So that's where 10 is in relation to 9 years. And all of this should make sense if we've been over here with our stats for the better part of a semester at this point. So there we are with about 34.5%. That's the closest to what we got off of our calculator. Moving over to number 15, this is basically the same question, but this time we have a company producing a soap powder labeled Giant, size 32 ounces. And the actual weight of the soap is a normal distribution at 33 ounces and a standard deviation of 0.8. Now, the reason you would do that is because with a standard deviation of 0.8, you know that some of the boxes are going to be underweight, and you want to minimize the number of underweight boxes. Most consumers won't sue you if you have more than what is labeled, but they will sue you if you have less than what is labeled. So this is, again, like a similar problem. It is a number which is 33. We're interested in underweight, so less than 32 ounces would be underweight. The mean is 33. The standard deviation is 0.8. That gives us a z-score of 1.25. We'll do the same thing over here. We're going to change that x. We're going to write this into, this is the weight of the soap. So we want to know that the weight is less than 32 ounces. And that would be, a z less than negative 1.25. We can go ahead and grab our calculator again. Second distribution, normal CDF. We're going from 0 to 32 ounces with a mean of 33 ounces and a standard deviation of 0.8. That'll give us 10.56. 10.56%, which are 0.1056. Over here, we'll fill out our curve again. If our mean is 33 and our standard deviation is 0.8 ounces, well, then that would mean that 32 would be just right over here, right around negative 1.25. Again, shade to the left of that because we want to know less than 32 ounces. And we'll look for a correct answer choice. That looks like this one, 1056, 106. So that's our 15. Moving over here to 16, we've got a normal probability plot. For the total annual cost to attend 126 top colleges in the country in 2005. So what is true about this? If you take a look at this data, look at the shape of it, it's kind of all, these are all mostly in a straight line on the left side. Let's highlight that. And then it takes a sharp turn upwards. So a lot of times we don't really talk about what these are supposed to do or what these look like, but we should take a look at them now. Here's the example of what a normal distribution looks like. Everything's kind of clinging to that straight line. Over here with a right skewed distribution, you have this bow upwards. Left skewed distribution, you have this downward bow. If you have short tails, you're going to create like an S. If you have long tails, this doesn't show it very well, but it's kind of like the backwards S. That's what long tails look like. So the best one here would be this right skewed distribution. So our answer should be the data are clearly skewed to the right. Now I'm having second thoughts about this. Now, if I take a look at this shape again, let's take a better look at what's going on here. 0 would be the mean. So the mean is right about here. And on this side of it, everything is very extended. Notice from the mean all the way to the minimum goes from about 30,000 all the way down to 0. Whereas over on the right side of it, all of these are very much close together. So from 0, so because these points on the right side that I've highlighted in yellow, these are really close together. This is a range of about, I don't know, $5,000. And then from here on to the left, this is between, $35,000 and $0. This is a very long on the left side. So this long on the left side makes me think that we're actually looking at skewed to the left data. So maybe I'm reading this stuff incorrectly. Let's take a look at this left skewed. The plotted points appear to bend down on the right side of a normal line, indicates a long tail to the left. And so what I'm looking at here, and I should have really checked this before we got to the video, is that these over here have the z-score instead of on the vertical axis, on the horizontal axis. Really, we should be looking at a chart like this. So I think I'm going to leave this one here. We don't need this one anymore. But for these, when we have the z-score on the vertical axis, this upward bow is a left skew and not a right skew. And this downward bow would be a right skew. So that kind of solves it here. Let's look at 17. Sorry if there was a lot of confusion on that one. And 17 says a researcher wants to determine the rate of water flow over an experimental soil bed can be used to predict the amount of soil washed away. So notice that we are predicting the amount of soil washed away, and we're starting with the rate of water flow. That's what we're controlling. So really, the explanatory variable here should be the rate of water flow, and this predicted the amount of soil washed away. That's going to be our response variable. So in this study, the explanatory variable should be the rate of water flow. Number 18, we have a study in the effects of television on child development measured how many hours of television each of 125 grade school children watched per week during the school year and each child's reading score. Which variable would we put on the horizontal axis? So the horizontal axis of a scatter plot is always the explanatory variable. So now we're going to have to read to see which one is the explanatory variable. So we're going to find the effects of television on child development. So we're measuring the number of television and the child's reading scores. So the effects of television, okay, that is going to be our explanatory variable. And on childhood development, that's going to be our response variable. So our explanatory variable should be on the horizontal axis. So whichever television is here, and I think it's this one, is the hours of television. And that is because it is the explanatory variable. That should be on our horizontal axis. 19. The following scatter plot represents data on wine consumption and the death rate from heart attacks on 19 developed Western countries. So we can see as wine consumption increases, the number of deaths per 1,000 per year, well, that decreases. So if one variable goes up or increases while the other variable decreases, that's going to be a negative correlation. So we can take a look and we can see that this is negative correlation. So that helps us a lot because now we know that R has to be negative. Now, as far as the value of R, what I like to do is I like to go ahead and just kind of shade in all of the points here and see how wide is what I call is the band. And if I take a look at this, what's the distance or how wide is this yellow shape? Kind of looks like a little banana slug now, but how wide is this? Well, the answer would be it's not a very wide band at all. In fact, you don't need a whole lot of imagination to see this horizontal or this diagonal downward sloping line that would basically connect all of these points. If I was going to draw that correlation, the regression line here, I'd probably do something like this. It's as close to as many of these points as possible while still staying inside of that yellow band. Since that yellow band is very narrow, or it is not very wide, probably your best answer would be something with a correlation close to -1. So this -0.84, that's clearly the correct answer in this case. And closing out this video, we have a bivariate data set A has correlation of 0.95, and the second one has data set B has a correlation of -0.95. Now the trick here is knowing that you can't really tell based on correlation whether or not the data is actually best modeled by a line. Perhaps it's best modeled by a curve. Just looking at correlation wouldn't tell you that. So a linear model does a better job of describing the relationship. Well, we can't tell which one does which one is a better linear relationship without looking at that scatter plot. It could be that data set A is linear and data set B is not very linear. And that kind of leads us to over here. This looks like our correct answer for letter E. You can't tell whether either data set is best described by a linear model until you examine the scatter plots. Yeah, there is no single number that will tell you whether or not a linear model is the best model. So a mistake has been made. R cannot be negative. We all know that that's not correct. We just saw R was -0.84 over here in question 19. So that's the end of our second part of this video, numbers 19 through 20. And we'll see you next time when we look at the rest of this statistics practice test.